I've got two reactions up on the board right now. One of them is a fission reaction, one of them is a fusion reaction. Can you tell me which one is which? Great. Yeah. How do you know the top one is fusion? You're correct, by the way. Top one is fusion, the bottom one is fission. How do you know that? Right. We're fusing together two light nuclei to make one heavy nucleus. Whereas in the bottom one, we are taking... Yes. Fission means splitting. Okay. So we're taking one heavy and splitting it into two light nuclei. Now, there's some neutrons involved here and some energy involved here and so on. And that's important. All that stuff's important, but it's not so important in determining what type of reaction it is. We just want to look at the bigger nuclei. Okay, do we take two of them and fuse them together, or do we take one of them and split them apart? That's the difference between fusion and fission. Now, what is it? I mean, we know, we talked yesterday about the energy that's generated here, and the energy that's generated in each of these reactions is not huge. So what is it that produces so much energy? Whether we're talking about a nuclear explosion or whether we're talking about the energy generated by a nuclear fission power plant, how is it that we get so much energy out of this when there's not very much energy produced in that single reaction? We got to get a lot of reactions taking place, right? In the second case, the fission reaction, it's the neutron that is combining with the uranium-235 that makes this happen. So what we want to do is take these three neutrons that we get down here as products or as daughters and cause them to get absorbed by three more uranium-235s, which will cause 9 neutrons, which will cause 9 more reactions, which will cause 27 more neutrons and 27 more reactions, and so on and so on and so on. That's a chain reaction, as Kyle called it there, because the products of one reaction cause more reactions. Now, in the first one, this fusion reaction, we need to pump energy into this to make it happen. By the way, what form is that energy usually in? Usually it's going to be in the form of heat. Although it doesn't technically have to be, it would usually be in the form of heat. We pump enough energy into it to overcome the repulsive force between the nuclei there, the hydrogen and the hydrogen. Okay, when we do that, it overcomes that repulsive force. They fuse together to produce this, a neutron and some more energy. And then some of this energy maybe goes into making more of these hydrogen fused together, more of these reactions take place. This is the dominant reaction in the sun. Fusion, that is. This is not the exact fusion reaction that takes place in the sun. It's slightly different, but fusion is that dominant reaction that takes place in the sun and generates our energy. If we were to look at both of these reactions, fission and fusion, can you tell me which reaction would generate more energy? Which single reaction would generate more energy? It would be fission, which is a little bit counterintuitive, right? Fission would generate more energy. We think fusion, well, that's a much bigger reaction. Fusion generates more energy, right? Well, it does when we compare apples to apples, right? What do we mean by that? Right. So fusion releases more energy per unit mass or per kilogram, but you recognize that because fission has so much more, a single reaction that is, has so much more mass, 236 protons and neutrons versus 4 protons and neutrons. You take enough hydrogen to make 236 protons and neutrons, you're going to get more energy out of it. But that's when you're comparing kilogram to kilogram, when you're comparing apples to apples. A single reaction, because there's so much mass involved comparatively in a fission reaction, you get more energy. But when you compare kilogram to kilogram or any mass to any mass, then you're going to get more produced in a fusion reaction. If there was some kind of nuclear disaster in Okotoks, and you happen to be not around at the time, which is good, you decided, oh, I want to come back. 5 years later, you decide to come back. Okay, which reaction would be safer? Which reaction would be safer if 5 years later you decided to come back? Okay. Right. Yes, yes. They're relatively speaking harmless compared to the products of fission. These are highly radioactive, whereas the fusion products are relatively harmless. We don't want to ever say harmless, right? But relatively speaking, relative to the other ones, harmless. Hey, make sense? All right. Today I want to take a look at a couple of new terms and use those terms to describe the energy that's released in the reaction, to calculate, in fact, the energy that's released in the reaction. Let me first define mass defect. When either a fission or a fusion reaction takes place, there will be some missing mass. Mass will disappear. Remember we talked in our last unit about Einstein's energy mass equivalence? Mass and energy are really two different forms of the same thing. So this isn't hugely surprising anymore. It was in our last unit, the fact that we could change mass into energy and change energy into mass. But now we know that that can happen. When a nuclear reaction takes place, some mass just disappears. But it's not destroyed, it's just changed into energy. The missing mass, the mass that disappears, is the mass defect. Now, we're going to define, and that results in the energy that's released that we'll talk about in just a second. That's the mass defect in the context of a reaction, the missing mass, the difference in mass between the products and the reactants, or the daughter and the parent nuclei. But we can also describe mass defects in the context, mass defect that is, in the context of a single nucleus. Now this is kind of wacky. Okay? In the context of a single nucleus, we can say that the mass defect is the difference in mass between the nucleus and the nucleons. Just hold off on writing this for a second, okay? I'll give you a chance. The nucleons are the protons and neutrons. We've talked about that before, right? The difference in mass between the nucleus and the nucleons. So let's say there's 30 people in this room. Okay? Let's say there's 30 people in this room. The analogy is there's 30 nucleons in this room, 30 protons and neutrons in this room. And each one of us has a mass of 50 kilograms for argument's sake, okay? Odds are we all, or at least most of us, have a mass that's bigger than 50 kilograms. But let's say it's 50 for the ease of math. Okay? 30 people, 50 kilograms. What's the total mass of the nucleons? What is it? Yeah, 1,500 kilograms, right? 1,500 kilograms. Well, if the mass of the nucleons is 1,500 kilograms, guess what? The mass of the nucleus is 1,501 kilograms. The nucleus, that is the sum of all the parts, weighs more than the individual parts combined. The nucleus has a mass of a certain value. Sorry, the nucleus has a mass of slightly less, I should say. So if the mass of all the nucleons combined is 1,500 kilograms, then the mass of the nucleus is 1,499 kilograms. Which is crazy. The difference is in how the energy is processed. It's called binding energy. We'll talk about in just a second here. So the difference in mass between what makes up the nucleus and the nucleus itself. The nucleus itself will have a mass that's slightly smaller than the mass of what makes up the nucleus. That's in the context of a single nucleus. That results in, or that causes, the mass defect in a reaction, which is the difference in mass between what we start with and what we finish with. We lose mass in a reaction because there's a recombining of protons and neutrons during a reaction. And as it does that, that mass defect in the context of a nucleus manifests itself in this reaction. Now you can write this down. When it comes down to it, listen, when it comes down to it, if you remember this, like that's pretty much going to take care of it, right? Okay, the mass defect shows us that the nucleus weighs less than what makes up the nucleus, and it shows us that the daughter, or you can call it the product if you want, weighs less than the parent or the reactant. So what? So what? So we got a little bit of missing mass. Well, we said when we described these fission reactions and these fusion reactions is there's energy release. Not very much in a particular reaction, but there's still energy release. Where does it come from? Well, if we lose mass, if we're missing mass, then it comes from the missing mass. That missing mass is converted to energy. We can define that energy as binding energy. Now, in the context of a single nucleus, it's kind of a weird definition, but listen, I wouldn't lose too much sleep over binding energy in the context of a single nucleus. Okay, what's more important is the definition of binding energy in the context of a reaction. It's the energy that gets released. So if we take the mass defect and we multiply it by c squared, E is equal to mc squared, then we're going to get the binding energy, the energy that's released in the nuclear reaction. Okay, there's lots of little things here, but I would suggest to you that if you focus on what's circled in purple there, you're probably going to be okay. All right, let's take a look at a couple examples here. The first one is probably the more straightforward one, the simpler one. It says determine the binding energy in the following nucleus. Ask yourself this: where does binding energy come from? Mass defect. So what do we need to find to get the binding energy? The mass defect. How do we define mass defect in the context of a single nucleus? It's the difference in mass between the nucleus and the nucleons. Yesterday, I texted you a table with some masses, including the mass to a high degree of precision of protons and neutrons, and also the mass of barium-141. I'll ask you to refer to that little table that I texted you now. You will find that the mass of a proton, as I texted you yesterday, was 1.67. 1.67, this is what it is on your data sheet, 1.67, but we need a higher degree of precision for these questions. 1.67207816 times 10 to the minus 27 kilograms. How many protons are there? There's 56, right? 56 protons. So that gives me a total mass of protons of 9.363637,696 times 10 to the negative 26 kilograms. So this is the mass of all my protons. The mass of a neutron, as given to you in that table that I sent you yesterday, is 1.6743839 times 10 to the minus 27 kilograms. It's slightly heavier to the fourth significant figure than a proton is. To 3 digits, it's the same mass. But to 4 digits, the neutron is slightly heavier. Now, how many neutrons do we have here? 141 minus 56 gives me 115. No, it doesn't. Should be 85. So if we take that number, 1.6743839 times 10 to the minus 27 times 85, that gives me 1.423222632 times 10 to the minus 25 kilograms. We add those up to get the mass of the nucleons. Since I did this wrong on my answer key, just give me a second here. 9.36363769 times 10 to the minus 26. Gives me a total mass of the nucleons of 2.359590008 times 10 to the minus 25 kilograms. There's the mass of the nucleons, right? What's the mass of the nucleus? The total mass that was given to you of the nucleus. It was given to you as, in that table, the nucleus of barium-141 is 2.3391792392 times 10 to the minus 25 kilograms. So you can see that the nucleus is slightly lighter than the nucleons. Okay, let's subtract those and get the mass defect. We get 2.04108408 times 10 to the minus 27 kilograms. What are we going to do with that? What are we going to do with the mass defect? Anyone? Now comes the easy part. We're going to find the binding energy. We're just going to say E is equal to mc squared. So there's your mass defect times the speed of light squared. We get a value of 1.84 times 10 to the negative 10. And the units for that would be joules. So it seems a little bit ugly up there, but only because of the number of decimal places. If these were whole numbers, this would be so short and easy. All you're doing is subtracting numbers, adding and subtracting numbers, right? Well, a little bit of multiplication, I guess. Get the mass of all the protons, there's 56 of them. Get the mass of all the neutrons, there's 85 of them. Add them up. So get the mass of the protons and neutrons or the nucleons. Then you get the mass defect. So subtract from that the mass of the nucleus. Okay, you get the mass defect in red. And then multiply the mass defect by the speed of light squared, and we get 1.84 times 10 to the negative 10 joules. Let's take a look at the second one now. Determine the energy released in this nuclear reaction. First one was in the context of a single nucleus, right? Context of a single nucleus. Difference in mass between the nucleus and the nucleons. The second one is in a reaction. So, what do we got to do in this one? We got to find the mass of the daughter and the parent, yes. So, let's get the mass of the parent first, or you want to call it a reactant, that's fine. Okay, the mass of a neutron is 1.67433839 times 10 to the minus 27 kilograms. The mass of a uranium-235, given to you on that table that I sent you yesterday, 3.9017292238 times 10 to the minus 25 kilograms. We add those up. The mass of the reactant, or the parent, is 3.918473077 times 10 to the minus 25 kilograms. So this is what we start with on the left side. This is the total mass. Would you expect the mass on the right side to be greater or less than that? Less, because we lose mass, right? That's the mass defect. The mass of krypton-92, again, given to you, is 1.5259741896 times 10 to the minus 25 kilograms. The mass of barium-141 is 2.3391792392 times 10 to the minus 25 kilograms. On a test, all of these numbers would be given to you somewhere, in a table, in a paragraph, somewhere. 3 neutrons. I got to multiply the mass of a neutron by 3. 1.67433839 times 10 to the minus 27. We add those up, and we get 3.915 3849458 times 10 to the minus 25 kilograms. Notice that that's ever so slightly smaller than the mass that we started with, right? We lost mass. We expected to lose mass. What do we call that missing mass? The mass defect. Well, then let's find that mass defect. It's the first one minus the second one, which gives us a mass defect of 3.0881312 times 10 to the minus 28 kilograms. Mass defect is always subtraction, right? You subtract the mass of the nucleus from the mass of the nucleons, or you subtract the mass of the products from the mass of the reactants, depending upon the context. And then energy is just mc squared. We'll take the mass defect and multiply it by the speed of light squared. And when I do that, I get 2.78 times 10 to the minus 11 joules, which of course we can convert to electron volts if we needed to.